Today we're looking at graphing using transformations. And so what we're doing is going through a whole process here. And the process was outlined previously in the previous section there, what we're calling this second method here, graphing using the RST method. So we're checking for a reflection, a stretch, and the translate. And so if you need those details, you want to take a look at the previous notes just to kind of outline what we've got going on with that and the parent functions as well. Okay, so with that as the background, now we're taking a look at how to go through that RST process. So I'm going to start off here with part B. Part A is just a straight line. So yeah, we could graph it. It's here just to show that you can even use the same process with a straight line, but for the most part, we're working with the other parent functions. So let's start off with part B. So we're trying to identify if we have an A, a B, an H, or a K. So here is the template that we're looking at here to identify where each of these values can be found, including that H or that K. So A is always outside the grouping symbols, B would be inside. H is inside the grouping symbols, and K is outside. So when we're looking at that, you can see that in part B we have an A. Now, where is the grouping symbol? Well, it's just sitting right on the X because only the X is being squared. There is no H, in other words, and there's your K. So the parent function is the parabola x squared. We identify the critical values. Here's the 5 inputs, -2 through +2, and the outputs. And then we check for a reflection, and in this case there is none. We check for a stretch or a shrink. That's the value of A that we're looking at here. So A is the 1/2. And so because that is a shrink, it's being shortened, which means that's affecting the y coordinates only, not the x coordinates, but the y coordinates, the up and down placement. So we want to take half of every y coordinate in this table. So all of the x coordinates stay the same. And then take the previous table of y coordinates and cut each of those values in half. So we have a 2, we have a 1/2, and to make it easier to plot, I'll just use a decimal value. And that's after the shrink. Now we take a look at the translation. T stands for translation, which means that you are moving it up, down, right, or left. This is where we look at the H and the K. There's the value of K, -2. So that means we're shifting it down 2 spaces. So again, that's affecting the y coordinates as we shift downwards. So we'll take each of the y coordinates from the previous table and decrease their value by 2. That's shifting down 2. So now our critical values continue to have the same x coordinates, but the y coordinates are changing yet again. So 2 minus 2 is 0, 1/2 minus 2 is a -1.5, 0 minus 2 is a -2, and then back up again. 0.5 minus 2 is -1.5, and then 2 minus 2 is 0. That's what we'll end up plotting here. The effect of this is that not only is it shrunk down, but it also looks wider than the parent function. If we were to graph the parent function for comparison, its vertex is at the origin. Let's see, 1, 2, 3, 4. I need that point here. This is the parent function. And so, yeah, we can see the vertex has definitely come down 2 spaces. But if you compare the width between those pairs of corresponding points, you can see that we have these points here and here, which are wider apart. These points here especially, 1, 2, 3, 4, 1, 2, 3, 4. The net effect is as it's shrunk down, it looks like it's flaring outwards as well. So the vertical shrink is also affecting the width as well. What we're doing here is really just focusing on the final result, the final transformation. So this is what I'm looking for at the graph. We don't have to graph the parent function. I'm not asking for that. Let's take a look at a few more cases. Here in the next example, here's a negative sign that's outside the grouping symbols. So that's the A. And then here we have the H. There is no K. So what we're looking at here is identifying first the parent function, which is the absolute value of x. And so we have our critical values. Again, inputs are -2 through +2. We're checking for a reflection. Yes, we've got a reflection here. So this is on the outside of the grouping symbol, which means it's going to flip upside down. That means we're going over the x-axis. That means a high value of y is going to be a negative value of y. So what we're doing is we're changing the signs on all of the y coordinates. So the x coordinates stay the same. Change the sign on all of the y coordinates. So now it's a -2, -1, 0, -1, -2. There's no stretch or shrink because the value of a is just 1. It's a -1. So it's not greater than 1. It's not less than 1. Here's the h, which is our translation. Now it looks like a -2. You might think that means left 2, but that's not the case. When you take this information out of the grouping symbol, you always change the sign. And so that means our value of h is in fact a +2. So we're shifting it to the right 2 spaces, which means that our x coordinates are increasing by 2. So this is the operation we're performing. The y's will stay the same, the x's will increase by 2. So the previous table has these for our x coordinates. -2, add 2, we're up to 0. -1, add 2, 0, add 2, 1, add 2, and 2, add 2. So those are the new x coordinates, and the y coordinates stay the same. So I'm going to plot just this final result here. This is the V-shaped graph that we expect to see when we have an absolute value function, but it's opening downwards because of that reflection that we had in the previous step. Now we really want to contrast the examples in part C and part D together because they both have negative signs, but they're going to show up in different places, and we want to see how we get that information in this next example. This next one is a bit of an odd one. It's less common to have a negative inside and on the x, so let's talk about this. When we're looking at this compared to our template, we want x right here to be positive. What that means is if there's a negative sign, we're going to park the negative sign here outside of this set of grouping symbols, although it's still inside the bigger set. And so that means we have to factor out a -1. Also, we want x in front and h in back. So we need to shuffle some things around. So first, let's move the x in front. Now that's a negative x, so move the sign with the x. Take the 1 and push it to the back. That's a +1, so move the sign with the 1. So as you look at this, you might say, yeah, there's the x and there's the negative in front of it, right? Well, not exactly. This x has to be a positive x, and we're going to park the -1 here as an outside factor. Now it's still inside the radical. It's still under the radical, but what we're doing is we are removing the -1 as a factor away from this binomial. So divide out the -1, factor out the -1, you have now a positive x, and then followed by a -1. That is the standard form we need. So now here x is represented as a positive x, and there's your multiplier. So this is the b. A would be found here outside the radical. Here's your h, and then there is no value of k. So we are not looking at the a, we're looking at the b. So notice the different placement in these two examples between where the negatives are found. The negative is outside the grouping symbols, and here the absolute values are the grouping symbols, versus when you have a negative sign inside the grouping symbols, and here we're talking about inside the radical as opposed to in front of the radical. That makes all the difference, and that means that what we're going to do is we're going to reflect it from right side to left side. That means our x coordinates are going to be changing signs as opposed to our y coordinates changing signs from the previous example. So starting with the parent function, it is the square root function, and for my critical values, we want to use only perfect squares. So 0, 1, 4, and 9 are the values we pick, because when we put that into the square root, we get answers of 0, 1, 2, and 3. Those are the square roots of those inputs. Then we're going to reflect by changing the sign on those x coordinates. So 0, -1, -4, and -9. The y coordinates stay the same. We have no stretch or shrink, because A is just 1. And then we're checking for the translation. And again, there's the H. Now it looks like a -1, but we don't shift it left 1. We always extract this information out of the grouping symbols and change the sign. So H is in fact a +1. That means we're shifting it to the right 1 space. That means our x coordinates are increasing by 1. So add 1 to each of your x coordinates from the previous column. So 0 plus 1, -1 plus 1, -4 plus 1, and -9 plus 1. The y coordinates stay the same here. And this is what we'll plot. All right, that last point is off the grid, so something like this. So remember with the square root function, you don't have arrows on both ends. You only have one arrow. And typically the parent function has a graph that is moving to the right and increasing to the right gradually, so the arrow's on the right. But because we reflected it from right side to left side, now the arrow is on your left, and the right has a termination point. All right, take a look at part E. Notice y is not by itself. So we have to get y by itself first. I need to shuffle some things around. I'm going to add 4 to both sides, so I have x plus 4 equals y squared. But if we want y to be on the left-hand side, we can just flip-flop the equation around. So y squared is on the left, and x plus 4 is on the right. And we want to take the square root of both sides, so we can have the square root function. And this is where we have a bit of a complication. Normally, when we take the square root, we would have a plus or minus. But that is not a function, and we'll talk more about that in a future chapter. So what we're doing is we are not using the plus or minus for the purposes of this graph. We're only using the positive version of the radical, like so, the positive radical x plus 4, so that it behaves like a function. So every input has exactly one output, and every output will have exactly one input. So we have, once again, our parent function of y equals root x. So we're using the same critical values as previously, 0, 1, 4, and 9 for the inputs, 0, 1, 2, and 3 for the outputs. There's no reflection. There's no stretch or shrink. We only have a translation. So again, we have a value of h. It is under the radical. It's in the grouping symbol. So when we extract that, it changes the sign. And we end up subtracting 4 from our x coordinates as we are shifting it left. So 0 minus 4, 1 minus 4, 4 minus 4, then 9 minus 4. The y coordinates stay the same. And there's the single arrow pointing to the right. There's the termination point on the left-hand side. So, as we look at these last two examples here, what's different is that the form of the equation is not ready for us to use the RST method. We don't have the grouping symbols. We don't have a way to identify the h and the k. The h should be inside the parentheses, but there are no parentheses. This is just a polynomial. Same with this one here. So we're going to change the form by completing the square on both of these. And we'll do that work right down here below in the empty space. So let me write down that equation again, and then we'll get started. So step number 1 is to make sure that your leading coefficient is 1, which it is here. In the next example, it's not, so we'll talk about how to deal with that. But step number 1, make sure your leading coefficient is 1, and it is. That's good. So now step number 2, if we had a constant term, I would push it over here, but there is no constant term. The next step is we have to add a number and then subtract it right back out again. Now, when we were completing the square a couple weeks ago, we would add a number to both sides of the equation to keep the equation balanced. But I don't want to add it on the left-hand side because I need y to be by itself. So that means we adjust the right-hand side by adding the number and subtracting it right back out again. What is that number? It's our magic number that we create by taking the value of b, dividing it by 2, and squaring that result. So here's the value of b. So 2 over 2, quantity squared. That gives me 1 squared, which is just 1. So we're going to add a value of 1 and then subtract 1 right back out again so this right side stays balanced. The reason for doing this is because these first 3 terms are now factorable. So we can factor that into x plus 1 times x plus 1. And we'll bundle them together because the factors are the same. So x plus 1 quantity squared. And there's your minus 1 on the outside. So here's your a, here's your h, and here's your k. Now we can use this method. So my parent function is x squared. Here's my critical values. Inputs are negative 2 through positive 2. There's no reflection. There's no stretch or shrink. We're going right to the translation. So here we have an h. Again, change the sign. So h is not positive 1. H is negative 1. And what that means for us is that our x coordinates have to be decreased by 1 because we're shifting it to the left. Let me do that first and then we'll come back for the k. So decrease each of those x coordinates by 1. So negative 2 minus 1 is negative 3. Negative 1 minus 1. 0 minus 1. 1 minus 1. And 2 minus 1. Those are the inputs. Those are the x coordinates rather. Now the value of k is a negative 1. That stays the sign. Don't change it. So k is negative 1. And that means for us that we're going down, so that means our y coordinates have to be decreased by 1. So subtract 1 from each of those y coordinates. So 4 minus 1, 1 minus 1, and so on. And that's what we'll end up plotting here. And for the final example, again, we're completing the square, but the math is a little bit more involved because the leading coefficient is not 1, it's a 2. So let's talk about how we go through completing the square. Again, let me start by writing down my equation. Step number 1, the leading coefficient has to be 1. Again, a couple weeks ago, we would change that by dividing away the 2. We'd divide the left side, we'd divide everything on the right side by 2. But I don't want to divide the left side by 2. I want to keep y by itself. So instead of dividing by 2, what we're doing is we're just removing a common factor of 2. So factor the 2 out. So you have your trinomial inside the brackets like so. Next we have to find that magic number. So I'm going to take this constant term and kind of push it here to the far right hand side because I need to find a number that I can add and then subtract right back out again, right here. So here's my thinking space. We want b over 2 quantity squared. My value of b is the negative 6. So negative 6 over 2 quantity squared. That turns into a negative 3 that we have to square, and that results in a positive 9. So I'm adding 9 and subtracting 9 right back out again. These first 3 terms will factor, like what we did in the previous example. And these last terms are just like terms, so they will combine like terms. Don't lose track of this factor of 2. That's still around. And don't lose your square brackets either, because when we factor this, we want to set this up as a binomial squared. So we have nested parentheses. This factors into x minus 3 times x minus 3. So we rewrite it as x minus 3 quantity squared. Again, the sign on the middle term is negative. That's why we have a negative here. X squared would give us x squared. 3 squared would give us 9. And a negative 3 plus a negative 3 combines to that negative 6. So if you foiled it out, you would get that trinomial. And then here you have negative 1 when you combine like terms. Now this is looking pretty good, but we're not quite done. And that's because the 2 that we factored out has to be distributed right back in again, so that we have 2 as my multiplier in front of the x minus 3. And 2 times negative 1 means my value of k is actually a negative 2. So here's the a, here's the h, and here's the k. So if we stop too soon thinking we're done, we're going to have the wrong value of k. We have to distribute that factor back in, and that changes the value of k. Now, we're ready to identify our parent function, which is the parabola x squared. Here's the critical values. Again, my inputs are negative 2 through positive 2. There's the outputs. We don't have any reflection. We do have a stretch or shrink. We have a stretch since a is 2. What that means is we're doubling the height. That means we're doubling the y coordinates. So the x coordinates stay the same. And we'll double the y coordinates from the previous column. So 8, 2, 0, 2, and 8. For the translation, we have both h and k. So we'll think about how that changes the x coordinates and the y coordinates. It looks like a -3, but when you take this out of the grouping symbols, you always change the sign. So h is in fact a positive 3. We're shifting to the right 3 spaces, which means our x coordinates have to increase by 3. So let's add 3 to each of our x coordinates. So negative 2 plus 3 is a 1. Negative 1 plus 3 is a 2. 0 plus 3 is a 3. 1 plus 3 is a 4. 2 plus 3 is a 5. And then the value of k is -2. We're shifting down 2. That means the y coordinates are decreasing by 2. So take the y coordinates from the previous column and subtract 2. So we get 6, 0, negative 2, 0, and back to 6. And that's what we'll plot. And there it is.